This is the 22nd lecture of the course MTH 204A, first section B. In this lecture we talk about basics of ring theory. So ring is one of the most fundamental concepts in algebra. The classification of all rings up to isomorphism is a far more delicate problem than that of groups. However, in this course we will be, as far as this course is concerned, in this lecture and in the next few lectures, we will be concerned with presenting the basic facts, the basic results of ring theory, which are very frequently used not only in algebra, in other branches of mathematics. So let me first give you the definition of ring. Many of you might have already seen it. So here we have a set R together with two binary operations denoted by plus and dot. So this is what we have, is said to be a ring. Said to be a ring if, first of all, R with respect to plus is an abelian group, R with respect to dot is just associative, in this course we are going to, all the rings that we are going to consider, they are having unity, that is, there exists. So this is one, this is second, the third condition is there exists an element 1 in R such that for every A in R, A into 1, 1 to A is A. So the reason for this assumption is very simple, that if time permits we will see that if a ring a ring doesn't have identity, then that can be embedded as an ideal inside a ring with unity. So therefore, and also the rings without unity are also not quite interesting from our perspective. Hence in this course we will always assume that any ring possesses a unity, and then we have this distributivity for A, B, C in R, A into B plus C, AB plus AC. Similarly on the other side, CA. So these are the two distributivity. Well, here so with respect to dot we just have only associativity and this existence of a multiplicative identity. So this operation need not be commutative. If this commutative, then we say R is a commutative ring. Okay. In this course most of the rings that we are going to encounter will be commutative. However, unlike this assumption, it is not, unlike this assumption it will be not just, so unlike this assumption it is not going to be justified if we simply say that all the rings are commutative, because there do exist important rings which come up very naturally, but they are not commutative. So that's why, let me again remind you that for this course our convention is that all the rings will contain a unity but need not be commutative. But again, that most of the rings that we are going to encounter in this course will be commutative. Okay. So a ring is basically a set together with these two binary operations such that these properties hold. Regarding this, as I have already told you that well, let me again say a few words. In some textbooks there are certain standard textbooks which do not include this in the definition of a ring, and then they further say that if a ring has a unity then it is called a ring with unity. But in this course here we have deliberately considered this condition to be included in the definition of ring. The reason is the following, that if a ring does not have an identity, then it can be embedded as an ideal, in a ring with identity. Yeah, so okay, so this one is called the unity. Well, it requires uniqueness, but okay, of course we will get into that. So the point that I want to make is, if a ring is not having a unity, then that can be embedded. Of course, these things you will I mean in precise terms you will see them later on, can be embedded in a ring with unity. So therefore it shows that it's in some sense enough to study rings with unity and their ideals. Okay, and also the rings. Yeah. So for this reason, we'll be having this assumption throughout. Okay. So here maybe unknowingly sometimes I said the unity. So saying something the unity is not justified unless we settle its uniqueness. So therefore let me immediately do that. So in fact these are very routine things, hence I should just leave them to you as an exercise. Some routine some very basic facts regarding rings. So the proofs are very straightforward, and in many cases the proofs are exactly the verbatim repetitions of those for groups and vector spaces. So first property is unity is unique. Unity is unique, that is, okay, so this is one condition, this is one fact. The proof is basically just like the uniqueness of identity elements in groups. So okay, and also the following properties one has the following properties. So as I said that I will be leaving the verifications to you. These are routine verifications, and in most of the cases the arguments are very, very similar to what you are familiar with. So for example, this is this 0, okay. Next, for every AB, so you see these are quite obvious. This type of things, this kind of statements you have already established for groups and vector spaces. So in most of the cases the same proofs will go through. Next, and then also we can consider this. Okay, so these are some basic facts about rings. So this says that the unity is unique. So therefore, from now on we can safely say that we can safely call it the unity. Okay, all right. So this is the definition of a ring, and some facts which immediately follow from the definition. Hence, now let's look at some examples of rings. We are going to see various examples, various interesting examples. So let's start talking about them one by one. Okay. So Z, Q, R, C. So these are, this is the set of integers, rationals, reals, and complex. So each of them forms string with respect to usual addition and multiplication. Okay. So these are again in most of these examples that I am going to talk about, the verification of these properties are are either obvious or quite routine. So, I am leaving the tedious job of verification to you, but here it is simply obvious. So, we do not have anything to do. Next, let us consider Zi. Zi is called the ring of Gaussian integers. So, it consists of all elements of this form, A, B belongs to Z. So, this is the complex number I. So, the addition, so this is clearly you can see is a subset of C. So, the addition and multiplication on this set is basically the restriction of the usual restriction of multiplication of C on the restriction to this sub collection. That is the usual addition and multiplication. Similarly, one can consider Qi. Okay. Similarly, one can consider Qi. So, it is easy to see that both Zi and Qi will be both of them will be rings. In fact, more generally, so what is I? I is nothing but a complex number whose square is minus 1. So, like more generally what we will do be considering is let D be a square free integer, be square free, okay. So, what does that mean? That no perfect square divides D. For example, 2 is a square free integer, 3 is a square free integer. So, now if D is positive, so let us adopt a convention for the time being. If D is positive, then by root D, of course, we mean we would mean the positive square root of D. If D is negative, then by root D we mean this. Okay. So, remember this is just a convention for this discussion. So, I mean that if D is negative, then that is how we will interpret, and we would like to consider these two collections A plus root D, yeah, where A, B in Z, and similarly we can of course talk about Q root D, where A and B will be from rationals. It is easy to see that this for any such D, this forms a ring with respect to usual addition and multiplication. That is easy to see, because if you have A plus B root D plus if you just want to verify the multiplication C plus root D, then AC plus BD, B small d times D, then what happens? AD, right. So, that clearly shows that this is closed under multiplication. Okay. So, therefore, so this generalizes Zi Qi. So, here as D we have taken, so if we take D as minus 1, then these two become Zi and Qi respectively. So, so thus for any square free integer D, we do have rings like this. In fact, we can further generalize this. So, recall that all that we need is like if you look at a typical element of this form. So, if you look at a typical element of this form, what you see is this D is a number in the, let us say here in the complex number whose square is D. So, basically D is basically the root of this equation, right. It's a root of this root D is nothing but a root of this equation. So, so it's a monic polynomial, it's a 2-degree monic polynomial, right. So, the following generalization, the following is a generalization of this. So, let me do that in somewhat generality. So, suppose that B is a ring, suppose that B is a ring and A is a subring. So, again let me tell you the meaning of subring. So, suppose R is a ring and S is a subset of R such that S is also a ring with respect to the operations induced from R. In that case we call S a subring of R, okay. We call S a subring of R. So, the definition is exactly same as that of subgroup or subspace. So, it is a subcollection which is in its own right, which is also a ring with respect to the operations induced from that of the bigger ring. So, suppose B is a ring and A is a subring. For example, so R is a Z is a subring of Q, Q is a subring of R, R is a subring of C, Z is a subring of Zi, Q is a subring of Qi, Zi is also a subring of Qi, okay. A lot of examples we can even see now. A is a subring, okay. Suppose let X belongs to B, well maybe put alpha, be such that there is a monic polynomial with coefficients from A whose one root is alpha, that is there exists a polynomial monic polynomial. So, let me rather do it in this way, alpha to the power n plus n minus 1 alpha to the power n minus 1 monic polynomial, maybe a naught. So, such that all ai's are from A. So, it is a monic polynomial with coefficients from A. So, we let alpha be such that there is a monic polynomial such that there is a monic polynomial which has alpha as a root, that is alpha so that is A1 alpha plus A naught is 0. Suppose alpha is such an element, for example here you see that D is such an element that there is a monic polynomial with integer coefficients, there is a monic polynomial with integer coefficients whose root is this quantity. In that case we consider, so A of alpha. So, what is A of alpha? A of alpha is precisely the collection of all members of B of this form A0, well I should not say A0 because these are used here, anyway let us use a different notation, B0 plus B1 alpha plus Bn minus 1 alpha to the power n minus 1, okay. Bn minus 1 plus alpha to the power n minus 1 exactly, because alpha to the power n is again can be expressible as a linear as a combination of the lower powers of alpha where each bi is in A. So, it is easy to see that this also forms a subring of B. So, in particular this is also a ring, it is a ring, in fact a subring of B. Okay. That is quite easy to see, like if you take the product of two such things, you will see that as soon as the power of alpha is at least n, then those things, for example alpha to the power n is the negative of this entire thing, right, then alpha to the power n plus 1 can again be expressible in terms of lower powers of alpha. So, therefore, this collection is closed under addition and multiplication induced from that of additional multiplications in B. So, this is a ring. So, here I will just mention mention the nomenclature and I will come back to that later on. So, suppose we have a ring and a subring, and if an element alpha satisfies this condition, that is there is a monic polynomial with coefficients from the smaller ring which is having alpha as a root, then in this case we will say alpha is integral over A. So, thus what we have seen is whenever we have a subring of a ring, then every element from the bigger ring which is integral over the smaller ring, for every such element we can for every such element this becomes a subring of the bigger ring. That is what we will see, that is what we have seen. Okay. So, in particular this is also a ring which you might have seen it earlier. Which you might have seen. So, this is basically like fix a natural number n, let omega be a primitive nth root of unity. So, what it means is, so omega is a complex number, primitive nth root of unity what it means is, first of all, omega to the power n equal to identity, and omega to the power m will not be identity if m is smaller than n. So, that is, so for example, let me give you an example, e to the power 2 pi I by n is a primitive nth root of unity, okay, and omega to the power m not equal to identity if m greater less than n, okay. So, or in other words, in the group of all nth roots of unity, this omega is a generator. See, if omega is nth root of unity, then certainly z omega is a ring, and also we can consider q omega, that is also a ring. So, what is the, so the collect, yeah, so this consists of all elements of this form a n minus 1 omega to the power n minus 1, each a I is from z, okay. Similarly, for this will be each a I will be from q. So, these are the typical, these are the special cases of this. So, all that we actually considering is, we are considering an element from the bigger ring which is integral over the smaller ring, okay. Whenever, as soon as we have that, then we do have, then we immediately obtain a ring, okay. All right. So, the next class of rings that we are going to consider are the matrix rings. So, we may take F to be Q, R or C, then consider. So, for natural numbers, for natural number n we consider M and F, okay. So, it's easy to see that this forms a ring with respect to usual addition of matrices and multiplication of matrices, okay, for every n. In fact, we do not even have to consider F to be this. If R is any ring, then for any n natural number n, this also forms a ring, okay. This also forms a ring, that is set of all matrices, collection of all matrices with entries from R, and the operations are usual, the usual addition and usual multiplication of matrices, okay. The important thing is, so why this, like the noteworthy difference of this matrix rings with those which we have encountered previously is this, that since matrix multiplication is not commutative in general, so therefore these rings are non-commutative rings, even if R is commutative. That is because of matrix multiplications do not commute. Non-commutative rings in fact, I mean, the most frequently encountered collection of non-commutative rings is so it is one of the most frequently encountered non-commutative rings. And then we do have a very natural subring of this. Very natural subring. So, like from MNR, what we can do is we can consider the sort of all upper triangular matrices. So, upper triangular, so given a ring R, so we consider all matrices of this form that okay. So, all matrices with entries from R which are of this form, since the multiplication of two upper triangular matrices will again be upper triangular, same for the addition. So, and the identity is also identity matrix which is the unity of this ring, this also lies here. So, it is clear that this is a ring and in fact a subring of MNR. Yeah. Okay. All right. Next, we proceed with with the rings of matrices. So, now I am going to consider that consider the matrix ring over. In fact, we will be considering a subring of that. So, subring of that, which we will call the ring of Hamiltonian Quaternions. Hamiltonian Quaternions. Okay. So, this is one of the very important rings of matrices. So, what we do here is the following, that we consider, so in this case, so R is going to be our, N is going to be 2 and R is going to be our field of complex numbers. So, we consider all matrices of this form A, B, minus B, A, okay. A, B are complex numbers. So, this is a subring. So, you can immediately check that by multiplying two matrices of this form, that this is a subring of M to C. Okay. This is a subring. This is a subring of M to C, and since the entries are like this, so basically this is what you can also write this ring as follows, that let us say you write A as alpha 0 plus alpha 1, alpha 1I, alpha 2 plus alpha 3I, minus alpha 2 plus alpha 3I, and alpha 0 minus alpha 1I, all matrices where alpha 0, alpha 1, alpha 2, alpha 3, they all lie in R. Okay. So, this is also another another description of the same ring, so, this is called the ring of So, this ring is called the Hamiltonian Hamiltonian ring or Hamiltonian Quaternions, the ring of Hamiltonian Quaternions. So, what is so interesting about this ring, let me say a few words on that. So, first of all, it is clear that here, so if you look at like, okay, let me leave it to you as an exercise, that is that that's in fact a very routine one. It shows that every non-zero element okay, before that, one thing you must be convinced by now is this is not going to be in general a commutative ring, because matrix multiplication is involved. However, just to for the sake of formality or for the sake of being precise, what you can do is you can pick up some suitable matrices of this form and check them they do not commute. Okay. And just to have a complete proof of just to have a concrete counter example showing that this ring is indeed not commutative. So, this is a non-commutative ring. So, however, this ring, so every element in this ring they has some inverse, this every non-zero element has inverse, every non-zero element of this ring has inverse. Okay. This is simply because of when you look at its adjoint. So, what is the determinant of such a ring? This is simply like if you see here or here, so it is mod A square plus mod B square. Okay. So, mod A square plus mod B square is 0 if and only if A and B both are 0. So, once otherwise the determinant is going to be non-zero, then you see that from this description that its inverse is also going to be of the same form. Okay. All right. But like this fact that every non-zero element is having an inverse, that was not the situation for the rings that we have encountered previously. Okay. For example, in Z, if you take 2, 2 does not have an inverse. Okay. And also in many other examples. Okay. So, every non-identity element here has an inverse. This ring is of course non-commutative, and another important thing is that so it is clear that this H is a real vector space. Okay. Real vector space, and we can intuitively have a feeling that the dimension of this vector space is 4. In fact, that is the case. Let me write down the basis. So, identity is 1. So, then let me first denote them I 0 0 minus I. So, this is for the time being denoted by I hat, but in literature we mostly we usually even drop this hat. Similarly, define j hat by the 0 minus 1 1 0, and then k hat is 0 I 0. Okay. So, now it is quite easy to see that any matrix, let us say this, can be uniquely written as follows: alpha times I2 plus alpha 1 times I hat plus alpha 2 times j hat plus alpha 3 times k hat. Okay. So, every matrix in H can be written uniquely as a linear combination of this. Okay. So, this it shows that there is a basis of the real vector space H. So, it is a 4-dimensional vector space. All right. And furthermore, if you want to see how two elements in this ring they are being multiplied. So, any two elements, let us say of this form. So, traditionally, I mean, like as a custom, we simply write alpha naught instead of alpha naught I2. So, it's actually tacitly mean that I2 is there. So, suppose we have an element of this form and we do have another element of this form. Then the product of these two elements is determined by the product and sum of the elements, sum of the product and sum of real numbers, and of course the distributivity, and like, okay. So let me explain it in this way. So like if we know how these elements, these basis elements, if we know that if how to multiply two of the two basis elements, then using distributivity and the usual operations in R, we can immediately find out this product, right? So again let me repeat that. So this is because that in this ring a typical term will be nothing but a term from here and then a term from there. We take their product. While taking their product, the coefficients are being multiplied in the usual manner, and then the basis elements, corresponding basis elements, they are getting multiplied. Okay. So if we know that how to multiply, if we do have a multiplication table for this basis elements, then using that, then with the help of that table, using distributivity and product and the usual laws of addition and multiplication in R, we can immediately find out this product. So now it's like it's imperative to, it's necessary to know how to multiply two such basis elements, and that's exactly given. We can immediately check the following. So first of all, I square j square k square equal to minus 1, ij equal to minus ji equal to k. So basically it's like this, I hat, j hat, k hat, it rotates along in this way. So I product of this and this will be this, then product of j and k, of course this will be k and j minus I, okay, j and k. Similarly k and I will be k, j. So you can immediately verify this, because these are not some abstract things, these are your very concrete matrices. You can immediately verify this, and once we have this table, then from that it is not difficult to compute the product of given two elements from this ring of quaternions. Okay. So it's, as I said, it's a non-commutative ring. It's a very important ring, and another thing is this 1 together with these basis elements. So these basis elements, if you see that they are closed under multiplications, and they have inverses. So therefore this basis consisting of 4 elements of this vector space, that itself forms a group. So this is our group of quaternions. Okay. So what is Q8? Q8 is nothing but the group of basis elements of H, this group of this very particular basis elements with the multiplicative group of this very particular basis elements. Okay. And I think it's also I should tell you is like its connection with SU2. That's also provides us with a very concrete visualization. So let me first leave this as an exercise to you, that every matrix in U, so this is a very routine thing, every matrix in SU2 must be of this form, of the form AB minus B conjugate, A conjugate. That's a routine verification. Okay, you can do it. So that is shows that this SU2, that is special unitary group, is contained to a priori means contained inside as a subset contained inside this H, okay. And remember, if such a matrix is in SU2, then what do you obtain? You obtain is mod A square plus mod B square equal to 1, or if you write this is in real and imaginary part, then what you must have is this alpha naught square up to alpha 3 square equal to 1, okay. So like therefore what we will do now is we consider a matrix in SU2, which we write it in this way. So how do I write it? Alpha 1I, then alpha 2 plus alpha 3I, and then here where I have minus alpha 2 plus alpha 3I, and there are alpha 0 minus alpha 1I. We given any such matrix in SU2, we map it to the corresponding alpha 4 tuple, okay. So it's easy to see that. So here these tuples, they have these relations among this alpha is having these relations among themselves. It's easy to see that this is indeed a bijection. So thus the bijection between this SU2 and S3, okay, the 3-dimensional real sphere. So yeah, the 3-dimensional real sphere. So let me draw the picture. So this is S3, consists of all points such that okay. So this is the 3-dimensional sphere. So this is a group. So this group can be thus geometrically identified by means of bijection with this very concrete geometric object, namely the 3-dimensional sphere. So remember that this consists of all unit vectors in R4, right? So namely, so if we consider this 1 0 0 0, so the standard unit, the unit vectors of the standard basis, so all these unit vectors in the standard basis, they are lying on this 3-dimensional sphere. So by means of identification, we will try to look at their images. Inside SU2, right? Because SU2 and this, they are in a one-to-one correspondence. So it's very natural to ask that what is the matrix which corresponds to this. Now that's quite easy. So 1 0 0 0, it will immediately tell you that 1 1, so 0 0 0, so it will be simply identity. So the first basis element corresponds to identity, and since I don't have time, let me just mention you that this goes to I, that you can simply do this verification, okay. So therefore this basis vectors can be geometrically perceived as on the sphere as the standard basis vectors, okay. So therefore in that sense it is so you can consider this basis as the standard basis of the space H, right? All right, and yeah, and one more thing, this identification enables us to consider SU2 can be thought of as the set of all unit vectors, thought of as the set of all unit vectors in this H. Okay. Remember, H is a 4-dimensional real vector space with, we have a concrete basis for this. A typical element can be written like this. So it is equipped with a very natural inner product, right? And with respect to the inner product, we can talk about unit vectors. So a vector is unit if and only if the square of these things, the sum of the square is 1, and that precisely corresponds to SU2. So thus the unit vectors, the collection of unit vectors in this vector space can now be regarded naturally as the group SU2. Anyway, so we have talked enough about this quaternions. So enough for now, we can come back to this later on. Now let me talk about other examples. So yeah. So the next class of examples we will talk about is a quite obvious class. So Z for any natural number n, this class of modulo classes, okay, modulo classes n with respect to this addition of modulo classes, which is denoted by this, and of course multiplication of modulo classes, this forms a ring, okay. And this is a commutative ring, and of course it's very natural to ask that which modulo classes have given a modulo class, whether it admits an inverse or not, and very elementary number theory shows, the elementary argument shows that a class has an inverse if and only if this is A is co-prime to n. Okay. Next let's now move on. So this was, I think, the fourth one. Now let's talk about the fifth one. So now let's talk about the rings of functions. So like in vector spaces, we look at the vector spaces of functions, because that, there we have seen that it indeed this function spaces are like function spaces are the one of the most richest sources of examples of vector spaces. Okay. So here also we look at function spaces. So let X be a set and R be a ring. So we consider all maps from X to R. Okay. So with respect to pointwise addition, and pointwise multiplication, this forms a group, this forms a ring. Okay. So let me again remind you, pointwise addition means this, similarly for pointwise multiplication. Okay. So given a set and any ring, the collection of all functions from X to that ring. So here this addition is the addition of two elements in R. So small functions that forms a ring, and as a special case of this ring, what we obtain is the following. So this holds for any set X and any set, of course non-empty set X we will be considering, and any ring R. So if we let R be arbitrary and take X to be 1 up to n, then this is nothing but, so then this is, then what we obtain is precisely Rn. Okay. So because any n tuple can be naturally viewed as a function from 1 up to n to R. Okay. In fact, more generally we can do the following. So given rings R1 up to Rn, So let us say we are given finitely many rings. Of course, what we are going to talk about that goes for arbitrary collections, but for now let us first look at what happens to the finite cases. Then we consider all functions from 1 up to n to this union of Ri's, all functions such that phi of I belongs to Ri for I. Okay. So we consider all functions whose value at the ith point lies in Ri. Then we can immediately see that any such function can be naturally identified with a tuple, okay, with a tuple phi 1 up to phi n. Okay. So any such given a function that gives us a unique tuple, given a tuple that it gives us a function here, function of this form. So therefore this collection, we can easily see that this forms a ring with respect to the, so in fact so this forms a ring with respect to pointwise addition and multiplication, and that exactly makes this Cartesian product a ring. Here the addition and multiplications are basically pointwise additions and multiplications. Okay. Let me again repeat so that you can understand this properly. So given any finite collection of rings, we make the Cartesian product. So here this might be, this Ri's might be same, might be different, that I don't care. We can make this a ring by considering pointwise multiplication and pointwise addition, okay, that we can simply do. So this consists of all tuples a1 up to an, where ai is in Ri, right. This consists of precisely all tuples of that form. Now any given tuple of that form can be equivalently viewed as a function of this form, okay. So you might wonder that this tuple description is easier to understand than why I am actually breaking my head to consider, why I'm breaking my head to consider this, which is relatively, not so obvious to see. The reason for this is that this description can be now further generalized to any arbitrary collection, which we are going to talk about now, because like this tuple thing, whenever the collection is finite, then you can talk about a tuple, right. But if the collection is infinite, what do you mean by a tuple? Infinite or even uncountable. So then therefore we have to switch, we have to view, like we have to switch to this description, okay. So for tuples we see these are equivalent. So in general case we will take this one. So that is, so suppose we are given an arbitrary collection of rings. So we consider all functions from I to union of Ri such that f of I lies in Ri for every I, okay. So remember that when I is finite, then these are nothing, these can be these can be immediately viewed as tuples, but when I is arbitrary, then there is no notion for tuples. So therefore there we have to switch to this, we have to consider, we have to take this perspective, because then they have to consider take this perspective, okay. Because like the earlier one, this simply doesn't make any sense there. So like for the sake of generality, for the sake of generality, we will keep, we will bigger tuples as functions of this form. This is exactly what we are doing here. So, this collection, this is called the Cartesian product of the family, okay, the Cartesian product of the family. See, in order to define this, we do not need Ri's to be rings. So, basically this goes for any arbitrary collection of sets, okay. So, for any given arbitrary collection family of sets, this is what is called the Cartesian product of this family. Now, when each member of this family is a ring, then we will see that this also becomes a naturally this also becomes a ring with respect to pointwise addition and multiplication. So, what that means is, given two functions f and g, f plus g is the function which is having the value at any given point I, okay. Since Ri is a ring, so here this addition means, so this is the addition, so for any I, so this is the sum inside Ri, okay. Similarly for the multiplication, okay. So, now we see that shows us for any given collection of rings we can consider, so this is called the product of this family, okay. So, the product is, again let me remind you, nothing but the set is the Cartesian product, and the operations addition and multiplication are just the pointwise ones. So, given this family of rings, this ring, that is the Cartesian product together with this is called the product ring, this is called product of this family, okay. So, this shows us, given any family of rings, then from that we can construct a bigger ring, namely its product. This is called the product, Ri is called the product. Okay. So, yeah, this shows that this shows us a way how to construct more and more bigger rings from given ones. Okay. I will now talk about just a few things and then stop. So, this is one we see. Then all right. Now let's look at some other, rings of some other rings of functions. So, like as we have earlier seen that given any set x and R and a ring R, all functions from x to R, that forms a ring, right. As a special case, let us say if x is n and R is maybe Q, R or C, then this is basically is nothing but the ring of all either rational sequences or real sequences or complex sequences, and where the operations is the natural addition of sequences and natural multiplication of sequences. So, as a special case of what we have seen earlier, we obtain that the set of all real sequences, set of all rational sequences, set of all complex sequences, with respect to usual multiplication and addition of sequences, each of them is a ring, okay. It is basically a special case of what we have seen earlier. Then another important rings of functions which I am going to talk about is rings of continuous functions. So, this is a very important ring which we will see later, which we will deal with later on. So, let's take X to be any metric space or more generally topological space. If you are not familiar with topological space, you can simply consider X to be a metric space, and you can consider all functions from X to R or C, again that does not matter, let us take C such that f is continuous, okay. So, this is called the ring of this is the Cx, the ring of continuous functions of the topological space. So, with since sum of two continuous functions again a continuous functions, product of two continuous functions again a continuous function. So therefore this is so this given a topological space, this ring of, I mean it's given a topological space, the collection of all continuous functions on X that forms a ring. Okay. So thus given in topological space a very natural ring is associated to that, namely its ring of continuous functions. So the point of considering this, of course you will encounter that later on, is starting from X we go to this ring Cx. This is since this is formed out of X, so this ring actually reflects, since it is formed out of X, so this ring actually reflects the topological or the topological structure of the underlying space. So this is an algebraic object. Then studying things like, as I said, that from X we go to Cx, then studying things on this space, sometimes this becomes easier, then we can get back to the original space X and draw some very influential conclusions. Okay. So basically this is like from a topological object we move ourselves to some algebraic object which is very naturally associated to that, and then we can apply all the algebraic machineries in order to obtain some useful information of the about the underlying topological space. So this is of course in a sense natural, because this ring is formed out of the underlying given topological space. Okay, now I think I am almost done. So okay, so this rings of functions continuous functions I have already discussed. All right, next is we can talk about polynomial rings. Thus we have talked about rings of continuous functions associated to any given topological space. So the next class of so again this is a commutative ring, right? Because the operation, because C is the multiplication of in C is commutative, right? This is a commutative ring. Okay, so I think the next class of examples that we should now look at is the polynomial rings, but maybe it's not a good idea to talk about that in this lecture because it will take some time. So we will do that in the next lecture. I will just end this lecture with the following remark that let's go back to Quaternions. So in the Quaternions, if you see that, all right, the Quaternions, so this consists of all elements of this form, then alpha 2 plus alpha 3i minus alpha 2 plus alpha 3i, so alpha and alpha 1i, okay, where each alpha I is coming from R. So you can further restrict your attention to those matrices of this form where alpha is coming from either from the rationals or integers. So therefore let me use these notations, HQ. So HQ is nothing but the collection of all such matrices where alpha i's are coming from rationals, and similarly HZ. Okay. So exactly in the similar manner, or in fact it is obvious, it does not require any separate argument, that these are also rings. Okay. So it is a collection of all matrices of this form where each alpha is coming from Z or Q. So these are also rings. In particular, in fact they are all subrings of C. Here of course like earlier you can show that every non-zero every non-zero element in this ring is it admits an inverse. So, both these are non-commutative rings because matrix multiplication is involved. So, here like the way we prove that every matrix here, the way we prove that here every non-zero element is having an inverse, the same argument goes here as well, but however that is not the case here. Like here you can easily find out matrices, non-zero matrices which do not have any inverse. Yeah, so like the Hamiltonian quaternions, you can also consider this quaternions over Q and Z as well. Okay, so I think I should stop now. Next we will talk about polynomial rings and complexification of rings, that shows that how to obtain more and more rings from given ones. Okay. All right. So, with that I will stop this lecture.